Hey guys, it's Mr. Lum, and sorry I can't be there today, but I made a recording for your lesson for today. So anyways, let's get started. Um, so just a few things right here, things from grade 10 actually, factors that affect reaction rates. They are temperature. If you increase the temperature, increase the reaction rate. We'll talk a little bit more about that later. Essentially what it's going to boil down to is that molecules are moving faster and therefore they're going to be colliding more. And concentration, if you increases concentration, there's more chances of collisions. And pressure is, if you increase the pressure, it'll increase the reaction rate. This one right here happens to only apply for gases. Yeah. Anyways, if there's no gas present in the reactants, then pressure will have no effect on the reaction rate. So you need to have gases in order to increase the reaction rate for that one right there. I'm going to skip over this nature of the reactions one. And then there's a catalyst. A catalyst is a special type of chemical that goes into a reaction that is part of the reaction, but then gets reconstituted, or in other words, it comes out of the reaction the same way it went into the reaction, and it makes the reaction faster. Again, we'll talk a little bit more how catalysts work later, but essentially catalysts go in and they come out of the reaction, but they make the reaction faster. And then back to this one right here, nature of the reactants, some things just react faster than other things. And there's explanations, like for example, sodium reacts better and faster than lithium. And we can say that it's the nature of sodium is faster reacting than lithium is. And there's like all these explanations, like sodium has a larger radius, it has a looser bond to its outermost electron, and therefore wants to give up its electron more. We can say all that stuff, or we can just kind of chalk it up to it's the nature of the reactants. Sodium reacts faster than lithium. Another thing is that surface area, the greater the surface area, then the greater the rate of reaction. This only applies to heterogeneous reactions. And if we can't remember what a heterogeneous reaction is, I like to tell people it's a reaction where you can see two things. Or another way you can think of it as it's a reaction where you, if I gave you an equation, you would see two different phases reacting together. Okay, so you'd have, or two phases, or two states of, two different states of matter. So getting back to this surface area, and we'll just ignore this bottom part right here ignore this thing right here for a second. If you have like a beaker right here, and it has an aqueous solution, like say example like HCl, and then you have like a chunk of metal in there, and this chunk of metal happens to be like aluminum. The surface area will play a big part in how fast this reaction proceeds, and the formula for this would just be something like HCl aqueous plus aluminum solid, and that reacts and turns into aluminum chloride and hydrogen gas. But the most important part is that you have this aqueous and solid, and therefore it'll be surface area will play an important part in how fast this thing reacts. If I were to give you another different type of example, like let's say if we took calcium nitrate, which is aqueous, and we added that to, say, sodium carbonate, which is also aqueous. These are two liquids that would be mixing. Therefore, surface area would not be playing a role in this one. Surface area would be an important thing in this one, and surface area would not be a factor in the reaction rate for this one up here. Okay, because they are two same states of matter, both aqueuses, and therefore it won't have any effect on reaction rate. Same thing if I had something like another example. Say if I had hydrogen gas reacting with oxygen gas. They're both two of the same states of matter, and that turns into water. They're both the same states of matter. Surface area won't be a factor for that. They're the same. Okay? You can't increase the surface area of one of these gases mixing with another one. So surface area won't, it only applies to something that is a heterogeneous mixture, where you can see two things. Now there is the one exception. Let me give you another example right here of an exception where you have two different states of matter. And that's going to be, say if you had iron oxide, FeO, iron 3 oxide, that's a solid, and you added that to aluminum solid. Okay, this will be a very important part of having surface area. Surface area would be an important part. And even though these two states of matter are both solids, I want to bring back to this first kind of thing. You have to be able to see two things. I can see the red powder of iron oxide and aluminum. Like, so if I had like a block of iron oxide and a block of aluminum, it only has this small amount of surface area to react with each other. Compared to if I ground them both into powders, they can react. So again, surface area only applies to heterogeneous mixtures. Okay, if it's two gases or two things that are aqueous, it will not work. Now, there is another exception. Say if you had two liquids, okay, so not dissolved in water, but like they're two liquids. Now, it comes down to, are these two liquids what we call miscible? What miscible means is that they can mix. If they can't mix, then surface area will play a factor. So imagine you had like a beaker like this, a really narrow beaker, and you put in one liquid, it fills up there, and then you put your other liquid on top of it. The only reaction that's going to happen is right here where these two liquids are meeting. And if you put it into a different type of beaker, one that was very wide, right? And you had like these two liquids right here. You have this bottom liquid right here, and it is unable to mix like water and oil. And it's unable to mix with this other liquid up here. This weird fat looking beaker would have a higher reaction rate because it has a higher surface area. These two liquids are touching in these longer places. Now, if the two liquids are miscible, that means they're able to mix. You'd only see one thing, and so surface area would not be playing a factor. Okay, that is one exception of that surface area kind of thing. Now, now what else plays a factor in how fast things react? Well, a big thing that determines how fast things react are what phase it is in. Okay, so if it's a bunch of solids that are mixing together, it'll typically react slower than if a bunch of aqueous things are going to react together. So say if I gave you an example like this, I said A solid plus B solid plus C, say liquid, turned into whatever, okay, D. Or if I had X aqueous plus B, or sorry, let's try a different thing, Y aqueous, and that turns into Z. If you had to make a prediction which one would react faster, you would probably say this one would react faster. This thing right here would react faster. Okay. Now why would you say that? Why does aqueous react faster than solids and liquids, for that example? So if I just erase this really quick, is that aqueous. So first off, let's talk about solids. So solids are like this block right here. The particles are moving slowly. They're not really going to be interacting with other solids very much, and they're just moving so slow that they're not going to be reacting very fast. Now, the nice thing about liquids and gases, for that matter, if I had to put gases, would be like right here. They're faster than liquids, but just slightly. But liquids right here, if this was a beaker, the liquids, the particles are bouncing around right here. Compared to the solids, they're just kind of vibrating. So the liquids are moving around, and gases, well, they're really bouncing around right here. Okay, so they're really, really bouncing around. Okay, so, and that allows liquids and gases to react faster than solids. Now, what about aqueous? Why is aqueous the fastest? Well, to give you an example of why aqueous is the fastest, let's take a look at something that would be in aqueous, or in other words, aqueous, again, if you remember, means it's dissolved in water. So let's imagine we had something like this, NaCl. So table salts, just sodium chloride, aqueous, dissolved in water, and we're reacting it with something like, say, like silver nitrate or something like that, also aqueous. Why does NaCl, aqueous, react faster than liquids and gases? Well, when NaCl is placed in water, it disassociates. That means before it even reacts, and it's just in water by itself, NaCl actually is already broken apart. It's Na plus and Cl minus. And so the water is doing a lot of the work for us, and that's why it helps things react faster. The water that the salt is dissolved in already has broken the salt up into Na plus and Cl minus. And since it's already broken up, it allows it to react faster. Like, say if we had NaCl reacting with silver nitrate, Ag NO3, the silver nitrate, which is also aqueous, would also be broken up, Ag and then NO3 like this. And it allows the silver and the chlorine to react because the water has done half the work. It's already broken up the ionic compounds. And so aqueous reacts faster than like gases and liquids. Now, we'll talk briefly, and this is pretty much the only time we'll ever talk about this, but an inhibitor. An inhibitor is a chemical that decreases the reaction rate. It combines with reactants to prevent them from reacting, and so therefore not part of the final products. It kind of like just inhibitors often just grab reactants so that they're unable to be part of the reaction. So it's like this way of decreasing the concentration of the reactants without actually decreasing the concentration. So yeah, but we're not going to really be using or talking about inhibitors, but I want to make sure that you understand they do exist. Things are present that can slow down reactions. Okay, so we're going to take a look at actually measuring reaction rates here in an experimental setting, and we're going to be doing this actually on Friday. We're going to do a reaction, and we're going to measure the reaction rates. And so here's the reaction right here. Before the reaction even starts, we start with 10 grams. After 15 seconds, 4.5. After 30 seconds, 2.5, and so on and so forth. And what we see here is that we're able to graph it right here. And just so that we kind of understand the graph right here, the reaction is going fast at the beginning, right at the beginning. We can see that it's going fast because how steep this line is. Okay, the reactants are really being used up in the first 15 seconds. In the very last 15 seconds, the line is getting pretty flat. So what that means is that the reaction is slowing down as time proceeds. So we can ask like a thing of like, using the graph, calculate the reaction rate at 30 seconds. You don't often see questions like this, and I'll kind of explain why. So when you use the graph and you want to find the reaction rate at 30 seconds, what you do actually, and this is a horrible line that was drawn right here, it worked better earlier, but it's supposed to be a tangent line that only touches this point at 30 seconds. So it's supposed to be like, I'm never going to get a straight line here, but it's supposed to be like this, okay? A tangent line, it touches the graph or touches that curve only at that one point, and you can kind of see it right there. But say if we did that right there, and we touched that tangent line perfectly at that 30-second mark right there, and how you measure rate is, or the slope, is you're taking the rise over the run. So what is the rise and what is the run? So the rise is like, well, it's going from 0 to 6. So it's going to be like, it's going up 6. And we'll talk about that. You can say that it's going actually down 6, would be like -6. And the run is, I think it's like 61 or 62 or something like that. I think I wrote the answer here. I wrote 63 right there is what I thought it was. And so that means the reaction rate is 0.095 grams per second. Now, like I said, why it's going down, why can't we write negative 0.095 grams per second? You can write that. You can also write it positive too, and but it comes down to the wording of it. So you can say, what's the reaction rate? And you can say negative 0.095 grams per second. It's totally acceptable. But what most people will write actually, they'll say, what is the reaction rate at 30 seconds? And they'll say, the reactant is consumed at a rate of 0.095 grams per second. Okay, and so they'll keep that a positive number, because when you say the reaction is consumed at a rate of negative 0.095 grams per second, it's almost like this double negative, and it kind of implies that it's increasing in mass when it's not. So we often keep things at a positive number, but technically both are acceptable. Now, what happens if it says like, I'm just going to erase this line that I drew. What happens if it says like using the time interval, find the rate between 45 seconds and 60 seconds? So in other words, what we're trying to do is we're just trying to find the slope of this line right here, okay, between that 45 and 60 second mark. And what that is going to be is that, well, it's going to be the rate is going to be the change in mass over the change in time. So what was the change in mass? Change in mass was 1/2 gram. What was the change in time? It was 15 seconds. And so when you do that, it's going to be 0.033 grams per second. So you can numerically see that the reaction rate is slower compared to at the 30-second mark. So this is the reaction rate at that instantaneous reaction rate at the 30-second mark. And we would even see that the reaction would be faster between the 0 and 15-second mark. We can calculate that. Okay, and why is my slide not progressing? Okay, hopefully this works. On that last one, my slide wasn't progressing, and I'm now re-recording. Anyways, well, starting here. Okay, moving on after that kind of stuff, we're going to be talking about collision theory. So collision theory is essentially a part of kinetic molecular theory. It's essentially what means kinetic molecular theory means particles are moving around, they're hitting each other, they're transferring energy, and this is actually how reactions collide, or this is how reactions occur, is by colliding. So what happens is one chemical hits another chemical. For a brief moment in time, they produce like this weird chemical, and then they actually split off and make their real thing. So to give you an example, like what is this thing? What is this little intermediary step, this activated complex? Let's do a reaction that we've probably seen before, and that is the production of water. Say if you take hydrogen gas and you combine it with oxygen gas, and it turns into water, like that, okay? And it's gas, gas, gas. Everything's gas. Okay, just to quickly balance it, I'm going to change the colors here. We'll put a 2 right there, and we'll put a 2 right there, like that. Okay, so we've seen this reaction before. Now, something that we haven't really seen before is like, so what happens here? So what it means is that you have 2 hydrogen gases. So if I drew a picture of, here's a hydrogen gas, they're usually quite small. Okay, and we have 2 of them, so I'm going to put another one right here. Okay, and it's going to combine and hit a one oxygen gas. So it's going to combine and hit an oxygen gas. And oxygen gas is O2, so that's why I drew 2 little oxygens right there. Now, when they actually hit, what's going to happen is this little thing kind of comes up here, and these things kind of hit here, and they form what is called an activated complex. So they form something that looks like this. something like that. And then this activated complex is extremely unstable. It lasts for a millisecond at the best, and then it splits apart and it turns into the water that we are more familiar with. I don't know why I did it so small, sorry. Okay. Now if I write some words next to it, what we have right here in this picture right here, we have two H2s. There's one of them, there's the other one. Here's our one oxygen. They combine and they form what is called an activated complex. This is where it gets a little weird. It turns into H4O2 for a millisecond, for just the tiniest fraction of time. Then after it turns into H4O2, it turns into two H2Os. We don't bother writing this activated complex in there because it's short-lived. So instead, we just draw the arrow right from here. We skip over the activated complex and just write the products. But this activated complex it's an important idea, and we're going to talk a little bit more about that later. But before, I want to talk about like what are the effects of concentration, and we're going to go through this because we've kind of talked about this already. The effects of concentration just simply mean that the amount of particles, the greater the amount of particles, the more collisions per second, the higher the concentration. So, or the higher the reaction rate. The effect of concentration just means if you have more stuff out there, then you're going to have a higher reaction rate. The analogy that I always kind of tell people is like, imagine that we have a soccer field. Actually, but let me back up for a second. First off, a reaction is two particles hitting each other, okay? So that's what a reaction is. Now, my analogy is like, imagine you have like, here's a big soccer field, and you have, here's a person on the soccer field, and they're blindfolded and they have earplugs in, and yeah. And here's my other person on the soccer field. They're also blindfolded and have earplugs in. And these people are instructed to run around the soccer field. Okay, and this person and there's like a fence on the outside so they can't go through the fence. So this person kind of runs around like this, and then this person runs around like this. And they're running around. Now, it's a big soccer field. What are the chances of these two people hitting each other? Yeah, they can hit each other. It's definitely a possibility, but it's a big soccer field, and they're probably not going to hit each other. Now, what happens if we stuck like a bunch more people out there? Like, so now we have 25 more people out there, okay? And they're all running around blindfolded, earplugs in, and they're just running randomly in random directions. Now we have a greater chance of a collision occurring, okay? Now, say if we increase the concentration again, and we have now, instead of 25, we have like 125 people running on that soccer field, blindfolded, earplugs in. Now we have a really good chance of seeing a collision occurring, okay? And that boils down to, if you increase the concentration, then you're going to be increasing the amount of collisions per second. Therefore, you're increasing the reaction rate. So let's now take a look at the effects of temperature. So the effects of temperature, if you increase the temperature, you're also going to have more collisions, and you're going to have better collisions. Now, what does that mean by better collisions? So here's an example right here of compound A, compound B. They hit each other, but they were hitting each other very slowly. So what happens? Nothing happens. They just simply bounce off each other. No reaction. Because they did not have enough energy to have a successful collision. So if you increase the temperature, not only are you going to have more collisions, but you're going to have more successful collisions. So let's bring it back to that soccer analogy again. Here's our soccer field. Okay, we have one person right here, one person right here. Instead, they are, same thing, blindfolded, earplugs in, so there's going around in random directions right here. Okay, and but this time we cool them down, or in other words, they're not running, they're just simply walking slowly. So one, if a collision is going to happen, it's much less likely a collision is going to happen. If a collision does happen between these two people and they're walking slowly, it's not going to be that exciting. They're simply just going to bump into each other and then go in different directions. So it would not be what we considered a successful collision. But if we increase the temperature, and now these people are sprinting, just absolute sprinting as fast as they possibly can, there is a more likelihood that eventually they're going to meet and collide. Also, when they do meet and they do collide, that is going to be a very big collision, and therefore we call that a big reaction would occur. So the effect of temperature is like, yes, the increasing the temperature will increase the amount of collisions per second, but also, almost more importantly, it's going to increase the amount of successful collisions. Okay, we covered a lot of this stuff yesterday. We're going to be looking at some enthalpy changes in chemical reactions. And it's going to be the total amount of energy that is within a system is what enthalpy is. The PowerPoint was better before. I don't know why this delta right here got dropped down. It's supposed to be up there. The change in enthalpy can be calculated by knowing the total enthalpy of the products minus the total enthalpy of the reactants. We went over this a little bit before. So change in enthalpy equals, I think yesterday I actually wrote change in enthalpy equals the enthalpy of the products rather than final. You can write final if you want. Minus the enthalpy of the, instead of the initial, you can also say reactants. Okay, so look at some of these things right here. So in endothermic reactions, the enthalpy of the products is greater than the enthalpy of the reactants. So again, for delta H, if the enthalpy of the products and minus the enthalpy of the reactants, what's going to happen is that since enthalpy of the products is going to be bigger, the change in enthalpy, we discussed this last time, is always going to be a positive number. The surroundings will feel cooler because energy will be absorbed, and if we were to graph it, it would look something like this. Okay, where the products are, sum up their number here, HP, say if we said this is 120, and this is 20 right here, this is HR. Change in enthalpy would be 120 minus 20 would be 100. And so let's imagine this is measured in joules, be 100 joules. Now, on the graph, this is where the change in enthalpy is. That's the change in enthalpy. And for right here, that would equal 100. Okay, now this is different than exothermic. Oh yeah, the other thing I forgot to mention is that energy is on the reactant side in your equation. Okay, this is different than exothermic because enthalpy of the products is less than the enthalpy of the reactants. Okay, and that always produces a change in enthalpy that is always going to be a negative number. And again, it's going to be right here. So if here's my HP, my enthalpy of the products, which is going to be less than the enthalpy of the reactants. Okay, and so let's give this number 270, and let's say that this one right here is 100. Okay, and so that means the change in enthalpy, it's going down. This number, the change in enthalpy is going to be a negative number. It's going to equal negative 170. Okay, the surroundings are going to feel warmer because the reaction is giving off energy. And yeah, and we talked about this. That's why I spent very little time on this kind of stuff. You should have this kind of stuff in your notes. Okay, let's take a little bit of a break. And I want you to do page 16, number 24 to 28. So yeah, put the video on pause and all that kind of stuff. And then when you are ready, I'm going to do the questions as well. Yeah, you please put the video on pause, do these questions right now, and then when you're ready, you can unpause it, and I'll be doing them with you. Okay, anyways, hopefully you put on pause and now you unpause it. Let's do number 24. I'm reading the questions for the first time too. So it says delta H is, I'm just going to write down some of the key components. It says delta H equals negative 25 kilojoules for the reaction that A turns into B. Okay, so it says A turns into B like that. Rewrite this equation to show the 25 kilojoule property properly on the reactant or product side, and then draw a graph of enthalpy and reaction proceeds, showing relative enthalpies and will the surroundings feel warmer and stuff like this. Okay, so it says rewrite this chemical equation right here of A turning into B, but incorporate and put in your energy, which happens to be that 25 kilojoules. So first off, is this a positive number or a negative number? It's negative. Okay, so is it endothermic or exothermic? Well, it's exothermic. Okay, so we're going to be writing A turns into B, and since it's exothermic, it's going to be releasing a bunch of energy, and so it should be plus energy like that, or in other words, A turns into B plus 25 kilojoules. Okay, so this is my equation with incorporating energy into that equation. Now it says, is this thing, does the surroundings feel warmer or cooler? Well, it's a negative change in enthalpy, so it's exothermic, so therefore surroundings should feel warmer. Okay, that's it. That's number 24. This is number 25. If a reaction absorbs 40 kilojoules of heat, what is the change in enthalpy? You don't have to do this. It's it's a kind of easy question. It absorbs, so here's your reactants. It absorbs, sorry, then let's imagine that this is your energy right here. Here's your reactants. It absorbs energy, so it goes up, and it absorbs 40 kilojoules of energy, and now it turns into the products. What is the delta H for this thing? Well, we just drew the delta H right here. It's 40. Delta H is 40. Like that. Okay, it doesn't ask if it's endo or exothermic, but it is endothermic. And yeah, so number 26. What is delta H for the reaction of C? Let me write this down. C plus 30 kilojoules turns into D. What is delta H for this reaction? First off, is this reaction right here endo or exothermic? Energy is on the reactant side, so therefore it's endo. Okay. And which have more energy, the reactants or the products? So this is endothermic. If you don't know like what it means, what has more energy, the reactants or the products, just graph it. Just graph it, and it makes so much sense when you graph it. We know it's going to be an endothermic reaction. That means it's going to look like this. Okay? Now, these are the reactants. These are the products. This is energy over here on the y-axis. Which one has more energy? Well, I think the products are a little bit higher than the reactants. So, which have more energy, reactants or products? The products have more energy. Okay? Draw a graph of enthalpy versus reaction proceeds. I did that already. It helped me find out what has more energy. Showing the relative enthalpies of the reactants and products and the change in enthalpy. Now, I could throw this thing in right here and just say change in enthalpy is 30. Okay? Positive 30, of course. Will the surroundings feel warmer or cooler? Since it's endothermic, the surroundings will feel cooler. And that's number 26. Okay? Number 27. I'm doing my questions all over the place. Number 27. Draw a graph of enthalpy versus reaction proceeds for R turns into P with 10 kilojoules. Okay, is that endo or exothermic? Well, energy is a product, so therefore it's exothermic. What am I doing right there? I don't want to rewrite that. And what else does it say? Oh, graph it. Okay, since it's exothermic, it's going to be right here, like that. And then this would be going down 10, like that. Okay, here is R, here is P, and yeah. Oh, and does it feel warmer or colder? It's exothermic, so it feels warmer. Okay, I need some more writing room, so I'm going to erase that question number 24 up there. And then we'll do that last one, and yeah, we'll move on. Where was my pen? There it is. Okay, last one, 28. When 1 mole of HCl reacts with 1 mole of NaOH to produce 1 mole of NaCl and 1 mole of water, let's write some of that stuff down. We have HCl plus NaOH produces, we'll keep it in the same order, NaCl and water. It's a 1-to-1 to 1-to-1 ratio. 59 kilojoules of heat is absorbed by the surroundings. Okay, so I want to kind of read that around again. It says 59 kilojoules of heat is absorbed by the surroundings. That means 59 kilojoules of heat went into the surroundings. that means it was released into the surroundings. It wasn't taken away from the surroundings, it was given to the surroundings. So this is going to be here, 59 kilojoules, like that. Okay. I know it seems they tried to fool you by writing absorbed by the surroundings. That means the reaction released 59 kilojoules, the surroundings absorbed it. If it said something like the reactants absorbed 59 kilojoules of energy, it would be an endothermic reaction. But no chemicals are absorbing the energy. The surroundings are absorbing the energy. Where did that energy come from? It came from the reaction. It's releasing energy. So this is an exothermic reaction. Draw a graph of enthalpy versus reaction proceeds, showing the relative enthalpies and all that kind of stuff. So same thing. Since it's an exothermic reaction, we know it's going to go like this. 59 kilojoules. And if you want to get fancy, you can write HCl plus NaOH up there because it's a reactant, NaCl, and water down there because it's a product. That's it. Okay. Okay. Kinetic energy distribution graphs. Kinetic energy is like the movement of like how much stuff is moving around. And a distribution graph is like if you graph the kinetic energy of every molecule in a sample, it would create a distribution graph. Now, a distribution graph is, I have an example right here what a distribution graph is. Now, and it probably doesn't make a whole lot of sense, but I'm going to go over, and we're going to make our own distribution graph. So let's do a graph right here. Okay, and we're going to do something a little bit more like we can understand it. We're going to talk about height. Now, we'll say, I don't know what the shortest person in the class is, but let's pretend it's 5 feet. Okay, and let's say the tallest person in class is like 6'5". So here's the 6'4" person, the 6'3", and you get all the idea. Okay, so how many people in the classroom are 5 feet tall? It's like one person. Okay, how many people are like 6'5"? There might be like one person up there. Okay, now how many people that are like 5'1"? Maybe we got one person. How many people are 5'2"? Maybe we got 2 people. Okay, how many people are 5'3"? We got maybe 2 people again. 5'4". Oh, now we got a lot of people that are 5'4". Okay, and then we have, say, 5'5". We got a bunch of people that are 5'5", a bunch of people that are 5'6". And we have a bunch of people that are whatever this height is. And this height. And then it starts to go down just a little bit. And we get this graph like this. And we got a few people that are tall. We only got that one guy that's 6'5". We have a guy right here, a couple people that are 6'2", a couple people that are 6'1" or something like that. 6 feet, 3 inches, 6'4", 6'5", something like that. And what happens is we get this, what is called a distribution graph. So on the y-axis, we have number of people. And then here we have whatever we're sampling. So in our case, it happens to be height. So we could do a graph that looks like this with all these x's, right? Or instead we could just draw something like this. Like that. Or in other words, it would look like this. It's the same thing. And we don't need all those x's in there. And this is what is called a distribution graph. Okay? So now we didn't measure height in people, We measured particles and how much kinetic energy they have. And that's what we did here. So kinetic energy, let's imagine there's 1 billion particles in our sample. One of the particles almost has no energy. One of the particles almost has like 1,000 kilojoules of energy, a lot of energy. But there are many samples that, like there's most of the samples have, what is that, 380 kilojoules of energy. You get the idea. It goes all the way up there. But they don't bother writing that. Okay? Instead, they just do like the percentage of the particles. So for this one right here, it happened to be 11% of the particles have 380 kilojoules of kinetic energy. A quarter of the percent of particles have 1,000 kilojoules of kinetic energy. A quarter of the percent of the particles in a given sample has almost zero energy. So this is what a kinetic energy distribution graph. So say if I have like a beaker right here, and there's some salt in there. There are trillions and trillions of molecules of NaCl. And when you touch it, they pretty much, it all has the same temperature. But on a molecular scale, some of those particles have a lot of energy, some of those particles have very little energy, but they all follow this distribution graph, which is considered to be a normal distribution graph. Okay? And that's what we have right here. So this is called a kinetic energy distribution graph. It's just saying in a sample, a couple of the particles will have a ton of energy, a couple of the particles will have very little energy, most particles will have somewhere in between. Oh, yeah, let me get rid of this so you can read it. Okay. Now, it also says that temperature is a measure of the average kinetic energy in a sample. Okay? And that's what temperature is. It's just a measure of the average kinetic energy in a sample. So if you want to find out where temperature is on a graph, on a kinetic energy distribution graph, it is just the highest peak, this part right here. That's the temperature right there. Oh, perfect. That's the temperature right there. Okay? Okay, now that we kind of understand that, here's a question right here. What sample, the blue sample, or the red sample, which one has more kinetic energy? Which one, sorry, let me rephrase that. Which one is at a higher temperature? So hopefully you looked at it and you're like, the red one has a higher temperature. Now why? It's because if we look at it, which one has a higher average kinetic energy? The peak. The red one has more of a higher average kinetic energy. This one has a lower amount of kinetic energy. So instead of kinetic energy, we could write like something like a temperature. This is 10 degrees Celsius. This is, I don't know, whatever this is, 20 degrees Celsius. So the red sample is at 20 degrees Celsius, and the blue sample is at 10 degrees Celsius. So why is the 10 degree one go higher than this one right here? It has more particles at this lower temperature, and so that's why this distribution graph goes higher here. Okay, so we're going to talk a little bit more about those kinetic energy distribution graphs. I want to take a look at, I'm going to draw a couple of graphs, and I want to see what the difference is. Okay, so let's draw, here's a graph right here. Okay, so we got one graph right there. Now, let's imagine we have this sample that looks something like this. Something like that. Okay, we have that sample, and we have, say, something like this. Question number 1 would be, which is hotter? Okay, hopefully you yelled out an answer. Maybe someone can ask David what the answer is. Green. Good. Hopefully you said that. Okay. Why don't I put a question mark there? It's not a question mark, that's the answer. The question mark goes there. Green is the answer. Which one is hotter? Green. Okay. Okay, so that went pretty good, hopefully. Okay, let's do another graph. Okay, I'm gonna make them a little bit harder. What's the difference between these two graphs? That one and that one. Okay. What about this? Which one is hotter? Maya. I don't know if you're answering it or not. Same temperature. They're the same temperature. Why are they the same temperature? It's because like their peaks are roughly at the same spot. They're the same temperature. Okay, so what's the difference? Why did I draw one like that? Okay. So therefore, if they're the same temperature, why are they different? Now, to answer that, we're going to go back to that idea of like, let's sample a couple of people and see how tall they are. So let's imagine we ask a class of like how tall they are, but the class only has like 6 people in the class, and this is what their distribution graph looks like. They got one short person, one tall person, and they have a couple of people in the middle right there, and then there's 2 people that are the same height. So that's what their distribution graph looks like. And in another class that has like 40 people, their distribution graph looks like this. They got a short person, they got a tall person, a couple people in the middle, and they have a lot more people that look like this. They have the same short person there. They have the same, the height of the tall person is exactly the same. The average height is exactly the same. Okay, what's the difference? There's more people in that class. This one has more people in the class. So what's this difference between sample blue and sample green? The blue one, blue is a bigger sample. So for example, the blue one might be 2 moles. The green one, green is maybe only 1 mole. That would be the difference between these graphs right here. Now, how can you tell like how much mass is in there? How many like that one is 2 moles? Well, technically it's the amount of area underneath the curve tells you the amount of area underneath the curve tells you that it's what the particles are. So to me, the area underneath the green curve right here looks to be about half of the area underneath the blue curve, and the blue curve goes all the way down to the bottom right there. So yeah, so if I drew another graph like this, actually like that, and see if I did another one like this, something like that, the blue would just be a tiny bit more mass or a tiny bit more particles than the red one. That'd be it. But yeah, so that's the big difference right there.